In this lecture, we're going to look at a new functional group that's highly related to the ethers. It's actually just a special type of ether, and it's called the epoxide. You may have heard a word like epoxide, that is epoxy, and for good reason. The epoxy resins have epoxides built into them because these are highly reactive. And I'll just emphasize this right away. They're highly strained and thereby highly reactive. Ethers. Now what they are is they are a cyclic ether built up of a three-membered ring. So a cyclic ether within a three-membered ring. Okay, so this is the structure I've shown here is the parent, what we call the parent epoxide. So what's kind of interesting about this molecule is that its bond angle is highly strained at about 100, and the bond angle is quite narrow. Its bond angle is far less, I'll just write this, far less than 109.5 degrees. Now 109.5 degrees is the typical tetrahedral center, an important angle to kind of note from Organic Chemistry 1. But anyway, so the parent epoxide looks to be far less than that. It's far less than 90 degrees. If we're going to constrain ourselves within a three-membered ring, we can't get there with even a 90-degree angle if we're going to be isosceles. So the molecule is strained. The reason why the molecule is strained is because it wants to be 109.5 degrees at the sp3 carbon atoms, but it's not. It's less than that. So it's strained due to small bond angles, let's say. So what they want to do is the epoxides want to relieve this strain by undergoing ring opening reactions. They want to release the strain, and that strain is called ring strain, by ring opening. Now, when we ring open, we're going to have to transform the matter somehow. So this opens up the possibility for some interesting chemistry and interesting new reactivity. So new reactions emerge from these ring opening reactions to relieve the ring strained. Now, the general conditions are really composed of two approaches. The first that we'll consider are basic reactions. Or let's say this, I'm going to rephrase this, sorry. Ring opening under basic conditions. So ring opening under basic conditions. Now, how this works is that, oops, sorry, I didn't mean to zoom in there. What we want to make note of here is that no H plus is available. We know that because we're under basic conditions. That is to say that H plus couldn't survive. So we don't have H plus at the outset of the reaction. Instead, a nucleophile directly adds to the epoxide. Not only adds, it ring opens the epoxide. Okay. Now what this looks like is, well, let's go ahead and just draw a reaction. I'm going to pick on a specific reaction because it's going to illustrate a point that we'll talk about in the next lecture. I'm going to have an epoxide with two methyl groups substituted on the left side of the ring, and then I'm going to leave the right side unsubstituted. That is, it simply has hydrogen atoms. So I'm going to say that this is substituted, and then conversely, the opposite side is not substituted. Now what we're going to do is let the nucleophile, and I'm going to define this as a good nucleophile. Many things have the ability to be a nucleophile under some circumstances, but this is particularly a good nucleophile. And I'm going to remind us that there's no substitution at the carbon atom added to the oxygen. Now, why am I highlighting the carbon atoms and not the oxygen? Well, the oxygen, having a delta minus, introduces a delta positive at either one of the carbon atoms, one being substituted and one being unsubstituted. The nucleophile is going to recognize the ability to sort of fit better at the site that's not substituted, and so it will attack there. Now, when it attacks there, it's going to push the electrons onto the oxygen. This is just like the ring opening reaction that we saw with the ether that was protonated. Here we don't need the proton. We're actually relying on the ring strain to engage the epoxide directly. Now, when we do that, we give rise to a new structure now. I like to draw it this way. The nucleophile is sort of added underneath that ring that popped open. So I put it at the bottom. The oxygen is now pointing at the top. And then our two methyl groups are on the left side, the carbon-oxygen bond that's still present. At the outset of the reaction, we had an oxygen with 2 lone pairs. After it absorbed the electrons from the carbon-oxygen bond, it now has 3 lone pairs. If you do the formal charge calculation, you'll show yourself that we have a group 6 element, minus 1 bond, minus 6 electrons by lone pairs, so it has a -1 formal charge. That makes sense because when we started the reaction, the nucleophile was negatively charged, and so something in the product needs to be negatively charged. Now that negative charge is shifted over to the oxygen atom, represented by the formal charge. What we do in this case is we then follow this up with what I call a then H plus step. We did this in the Grignard reaction in Organic Chemistry 1, but what this is called the workup. What we're doing here is cleaning up the reaction, providing an opportunity for the hydrogen to engage and neutralize the oxygen. But we have to draw the arrow from the negative charge to the positive, right? So we show the negative attacking the positive on the H plus, and we get to this structure here. So we have a neutral alcohol. Whoa, really misspelled alcohol there for a second. Neutral alcohol product. Now let me remind us just briefly what that then H plus step was. So then H plus is the workup. In the workup, we introduce H plus to neutralize any lingering negative charges. Okay. So what we can do now is consider what happens when we do this reaction under a different set of conditions, and that's going to be ring opening under acidic conditions. So ring opening under acidic conditions, what we do in this case, looks like I need to add some more pages here. Just want to make sure we have some continuity of thought. Sorry, should have done this beforehand. Okay, so ring opening under acidic conditions. What we do is we introduce H plus at the outset of the reaction. Okay, so I'm going to draw the exact same epoxide as I had just drawn, and we're going to have a nucleophile present. And let's say we've got a good source of H plus around, some sort of strong acid. What's going to happen in this case is the acid is going to react first. So here, The H plus reacts first. Now, how does it react? Well, the lone pair electrons on the oxygen will engage that H plus. Now, we have to be careful about our nucleophile selection to make sure that we don't pick something that will react with the H plus. Otherwise, this won't work. When we do that, we now have an oxygen with 3 bonds and 2 electrons. This is a group 6 elements. 3 minus 2 minus, 6 minus 3 minus 2 is going to give you +1. Okay, so now the nucleophile will engage this just like a protonated ether. We would call this a protonated epoxide. This is a little bit different though. In this case, the nucleophile is going to come and add to the left side. We actually don't see evidence for reaction at the right side. And that's going to give us, it's kind of difficult to draw, but I like to draw this sort of seesaw structure. We have the OH on the side that still has a carbon-oxygen bond. In this case, it's the right side. In the previous case, it was the left side. Then I like the nucleophile attacking underneath. That helps with the stereochemistry, which we'll discuss in a subsequent lecture. I'm going to draw those two methyl groups. They're sort of shifted up in this case to maintain the tetrahedral geometry at the carbon that received the nucleophile. Otherwise, this product is done. This is the product of the reaction. And so in this case, we saw, hopefully you can start to see why I chose these particular epoxides. There's one side that's unsubstituted and one side that is fully substituted. And whether you're under acidic conditions or basic conditions, you'll get a different outcome in terms of which side the reaction is attacked by. And so that's an important point. And again, we'll discuss that in a future lecture. What I want to do now is break from this. We're going to look at more details related to each of these specific reactions in the next lecture.